All right, so continuing on in the notes here, we were talking about the p-value. Note the p-value is a conditional probability. It's the probability of getting a sample like we got or more extreme than what we got, given the null hypothesis is true. So interpret the p-value for the Ricky Bobby example. Assuming the true proportion of shots that Ricky Bobby makes is 80%, this checks the condition box. There is a 0.0075 probability of getting a sample proportion of 64% or less by random chance in a sample of 50 shots. I think you could probably kind of maybe stop it right there, just a probability of getting a sample of 64 or less. But, the extra is nice, but not needed. The last step of the significance test then is to draw a conclusion. We're basically walking through a significance test kind of through a simulation. So we got to draw a conclusion based on that p-value. As I mentioned up here, and I kind of talked about before, we're trying to decide between these two things, right? Does he really make 80? I guess this is really going to be a mess. Does he really make 80% of his shots, and this sample just happened because of sampling variability? Or is it more likely that he doesn't make 80% of his shots and he got a sample of 64 because he actually makes under 80% of his shots? Well, this probability is the probability that this occurred. So if that probability is really small, how small? I don't know, 1%, 2%, 0.0075, or I should say 0.75%. If that's really unlikely, then I'm going to say, you know what? It probably didn't happen because of sampling variability. It probably happened because he really makes less than 80% of his shots. So we're trying to decide whether we should reject the null being Ricky Bobby makes 80% of his shots, or fail to reject it. Really, those are the only two conclusions we're going to make. We're either going to say, you know what? I'm going to reject the null and say he really makes less than 80%. Or I'm going to say, you know what? I don't really know if Ricky Bobby makes 80%. I just don't have enough evidence to call him a liar. We never prove the null. Never say we proved that Ricky Bobby... In fact, what's the probability that he really does make 80.0000000% of his shots? Pretty much zero. I mean, he probably doesn't make exactly 80% of his shots. He probably makes something maybe close, but we never prove the null is true. We just fail to find enough evidence against it. We just don't have enough to prove what we want. So small values lead us to reject the null, and large p-values lead us to fail to reject the null. So small lead to a rejection, large fail to reject. So we need to determine a cutoff for rejecting the null. We call this the significance level. As we have discussed in the past, I think did I move my screen here a little bit? Oopsie. Sorry. As we've discussed in the past, oftentimes 5% is a nice rule of thumb for this, but other values can be used. We call this the significance level, and we use the Greek letter alpha. So if your p-value is less than alpha, less than 5%, then we reject. We're saying 5% is small enough. If the probability of it happening is less than 5%, then I'm going to assume it didn't happen because of that. Sorry, that was a good awkward statement. So if the p-value is less than alpha, we reject the null and accept the reject the whole, accept the ha. If your p-value is bigger than alpha, then we fail to reject the null, meaning we never have enough evidence. We don't have enough evidence against it. All right, so let's draw a conclusion, and this is what our conclusion is going to look like when we start running a test. We are going to compare our p-value to the alpha value explicitly. Got to write it down on, it's one of those AP testing things. And if it's less, then we reject the null. And we're going to say this. This is like our statistical conclusion and why we make it. And then we're going to give our non-statistical conclusion. So our null was p equals 80%, and our alternate is that p is less than 80%. So if we reject the null, then I'm going to say this is not true, and I'm going to conclude that this is true. So I'm going to say we have convincing evidence that the true proportion of free throws that Ricky Bobby makes is less than 80%. We'll talk about how to construct that a little bit better down the road. For a second semester project in stats, Zenon decided to investigate whether students at his school prefer name brand chips over generic. He selected 50 students and had each student try both types of chips in random order. Overall, 32 of the 50, or 64%, back to 64%, of the students preferred the name brand chips. He performed a significance test using these hypotheses. So he's saying the null is that it's 50% against the null alternate that it's over 50. Basically, he wants to prove that a majority like the name brand chips. Well, if the percent is over 50%, then you have proven that it's over 50%, or you found evidence anyway. Where P is the true proportion of students who prefer name brand chips. The resulting p-value was, so here's my p-value. What conclusion would you make at each of the following levels? So I'm actually wanting to make this conclusion and not necessarily this one because I don't want to write too much. So for part A, if your p-value equals 0.0239, that is less than 0.05. Small p-value relative to your alpha means you reject the whole. And conclude the alternate. However, if our p-value is still 0.0239, but you use an alpha value of 0.01, now you fail to reject. So as you can see, fail to reject the null. As you can see, it matters what your alpha level is. You know, the alpha level is basically a measure of how much evidence you need in order to draw a conclusion. A significant test can be summarized as follows. An outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. I don't know where I got that. Or I mean, it wasn't mine. I stole it from somewhere, definitely, but I just liked it. If an outcome that would rarely happen if the null is true is evidence that the null is not true. Whatever. All right, a quick note about alpha, the significance level. You should set this before you run the test. It would be unethical to wait until you see your p-value and then say, well, I'm going to choose an alpha value of 0.01 because I can reject at 0.1. This alpha value is going to have a certain meaning here down the road. However, it's only going to have that special meaning if you pick the alpha value ahead of time, okay? Factors to consider when choosing alpha. If the null hypothesis is widely considered true and accepted by many people, perhaps you need strong evidence to change people's minds, so pick a low value. Low value means you need a lot of evidence. If rejection of the null hypothesis in favor of the alternate will cost your company a lot of money to change a new process, pick a low value because you really want to make sure that the null is false. The above things aren't true and consequences of making this mistake aren't so severe, you can just choose an alpha value of something higher. Or just go with the standard. You know, really, I'm not a researcher. I'm not a statistician either. I'm just a teacher. But I think in practice, a lot of times people don't even have an option. A lot of journals and publications force you to run it at a 0.05 level. So, as always is the case in statistics, mistakes are going to be made. We need to understand what mistakes can be made and understand the likelihood that they are made. So we're going to talk about type 1 and type 2 error. These are the two mistakes that could possibly be made. So a type 1 error is if we reject the null when the null is true. So I always remember these by looking at reality. The hoe is true. That's the type 1 error. So I always remember it like that. The null is true. And you make a mistake. Well, if the null is true, you should not reject it. Therefore, a mistake would be you do reject it. Here, we want to talk about the null being false. We fail to reject the hoe when the alternate is true. Now, that could also be worded as we fail to reject the null when the null is false. Whatever. That's a type 2 error. Describe a type 1 and type 2 error in the context of the Ricky Bobby free throw example. Type 1 error would be null is true. So we conclude that and we make a mistake. So he really does make 80%, but we conclude he makes less. So we conclude that Ricky Bobby lied about making 80% of his free throws when in reality he does make 80%. Type 2 error is this is false. So he doesn't make 80%, but we fail to find evidence that he doesn't. So we do not have enough evidence to conclude that he makes less than 80% of his free throws, when in reality, he really does make less than 80%. So which one is more severe? So we talked at pretty good length in class about which one of these we thought was more severe. In general, this is usually, these tests are kind of designed for the type 1 error to be the more significant one. It's because this is the status quo. This is kind of, it's your assumption. So if you make a type 2 error, you're just basically saying, well, you don't have enough evidence against the assumption, so I'm just going to assume that it's still true. Whereas this, your assumption is true, the status quo is true, and you're wrongly saying it's not. So usually a type 1 error is more significant, but you could argue about this. You could talk about consequences of each. But whatever. So here's a little table you can look at if you want. All right. 4 minutes, and we're going to talk about our court system and some probabilities. To be honest, this is something that you can kind of look through and think about on your own, but we talked about it at pretty good length. It's a nice analogy to make. You could read something in your book about it if you'd like, but I think it just plays out a little bit better whenever you're talking in class and it's a discussion type of topic. So let's just finish up with this section here. Oh, we do have another example. I'm just going to start another video and do these last two, this last topic and this last example.